Okay, so today we're going to talk about the Koopman operator. I'm going to take a slightly different approach to this lecture than I do with most of mine. Most of my lectures are often a little frenetic. And for this one, I'm going to be a lot more careful and a lot more considered because I believe that this topic needs a very careful and considered approach. So, why don't we go ahead and get started? So, what we have is a discrete time dynamical system where we don't know the dynamics. And what we want to do is we want to come up with some way of learning this system, and so the dynamic mode decomposition method turns this into a problem about not nonlinear dynamics, but rather linear operators. But linear operators can be a little tricky. You have to be careful about the vector spaces that you pose them over, and we want to make sure that we're very careful about this so that we get a good model at the end of the day. So the operator that we're going to be talking about is the Koopman operator. And maybe I've been watching a little bit too much Baumgartner lately, but why don't we go ahead and think of this as our painting. So the Koopman operator, it seems kind of magical. If you take a function from a function space, they call it an observable, and you apply the Koopman operator to this observable, then what you can do is if you evaluate this at your initial point, then what ends up happening is that we end up seeing that iterations of the Koopman operator being applied to our observable ends up advancing the state variable inside the observable. So iterated applications of the Koopman operator moves us from x1 to x2 to x3, but all inside of some function that we've selected, some g. So in this sense, it seems that the Koopman operator really does represent the discrete time dynamics in almost a perfect way. But if you look at a lot of literature, and sorry to say it, but a lot of literature from some of the big names in the field, you'll see that the Koopman operator has been a bit mistreated. And it is a little bit rough for wear. And so I'm going to go through here and I'm going to tell you exactly the pitfalls that these other data scientists have fallen into. It is natural for any sort of new field to have these sort of road bumps, and there's no shame in making these mistakes. You only really move a theory forward by just trying things, and that's what they did. Now, I should say that all their work from the data science perspective is fantastic. You see almost perfect recreation of your states and your snapshots, and most of the things I'm going to mention here really have very little bearing on the data science side of things, but they end up being very important from the operator theory side of things. So why don't we go ahead and get started? So the beginning of the, say, mistreatment of the Koopman operator really comes down to the canvas that we were using. And so when I say the canvas, I mean the vector space. Operators are posed over vector spaces, and their properties depend on the vector space you pose them over. You can have very similar looking operators that give the same formal equation, but they'll behave very differently over one Hilbert space or another. So one of the common misconceptions that you see show up in major works is that we can't use the L2 space for dynamic mode decomposition. And the reason for that is that it requires samples. If we are using samples, then at best we have a countable collection of samples. And L2 spaces don't care about countable anything. Two functions over L2 can agree over a measure 0 set, but everywhere else be completely different. So that means that over L2, we can't do any sort of interpolation of these points or approximation with these points because they have no meaning. That means we need to work on a proper function space. And so that is something like the Banach space of continuous functions over a compact set. This could also be reproducing kernel Hilbert spaces. Now, the space of continuous functions over a compact set, that's very nice. You can have very nice properties there. but at the end of the day, you don't really want to live there because there's no projection. There is very poor convergence. So what we would like to do instead is we would like to look at a reproducing kernel Hilbert space. And these are things like using the Gaussian RBF or the exponential dot product kernel. And there, sampling is very well defined. And another thing we have is that projections are very easy to compute. And finally, we see that computations with kernels are extremely easy. And if you watched my last lecture on the DMD algorithm, you'll see really just how straightforward it is. And so our canvas for this discussion is generally going to be a reproducing kernel Hilbert space. Now let's go ahead and take a look at a particular Koopman operator. Okay, so in order to talk about the Koopman operator I would like to talk about, let's take it inside and talk about a Koopman generator. Generally speaking, when we are talking about dynamic mode decomposition, we usually are thinking about some sort of continuous time system that we've taken snapshots of. We think of the Koopman operator as advancing us from one time step to the next, where the time difference between the two snapshots is the same. Koopman generators are sort of the infinitesimal version of this. And this comes straight from differential equations, and so we've talked about Liouville operators before, and in very particular circumstances, Liouville operators are Koopman generators. What I'm going to care about now is a dynamical system over R squared, and I'm going to be thinking of this as corresponding to the circle. So if you think about the unit circle, and this is given to us by cosine theta comma sine theta, if you take the derivative with respect to theta, then you see that cosine turns into sine of theta, and sine of theta turns into minus cosine of theta, and this can be rewritten as, say, x dot is equal to y, and y dot is equal to minus x, where x replaces cosine and y replaces sine. And so this gives you a dynamical system that will give you the trajectory of the circle. Now, for a lot of the computations I would like to do, it is going to be very inconvenient to think of this in R squared. And so instead, I'm going to use a model for R squared, and that is the complex numbers. You can get back from the complex numbers to R squared really easily, and that really just comes down to taking the real and imaginary parts of the complex numbers. What this is going to let me do is it's going to let me use a lot of factoring abilities for complex numbers, and it's going to let me do a lot of complex arithmetic. So in this case, I'm going to be taking a look at the complex variable z, and this is written as x plus iy. And if I take the time derivative of z, then the dynamics are going to give me y minus ix. And so this represents rotation in the complex plane. So in this case, we are going to move from the continuous time dynamics to discrete time dynamics by fixing a time step. So we're going to be going from, say, time point t1 to time point t2 by a difference of delta t. Now, what this means in the present context is that we're going to be rotating by a fixed angle. So that would mean something like rotating by pi over 4 or pi over 2, 45 degrees or 90 degrees. And we're no longer looking at R2, we're looking at the complex plane. We're going to have a real and imaginary part to our variables or our states, and now we want to find a collection of observables over the complex plane. This leads us to spaces of analytic functions and the Fock space. There are a lot of choices that we can make here, but in order to talk about an operator, we have to fix something. And so in this case, I'm electing to use the Fock space. The Fock space is an extremely well understood reproducing kernel Hilbert space. It is used in quantum mechanics, it is used all over the place, and it is a complex version of the exponential dot product kernel. So the Fock space consists of entire functions that can be written as a power series, an z to the n, and taking the sum from n equals 0 to infinity, provided that the coefficients, satisfy this inequality, where if you take their norm squared and multiply that by n factorial, the sum from n equals 0 to infinity has to remain finite. And this also happens to give us the square of the norm that we're talking about. So the kernel function that we're going to be using is the exponential function. It is the exponential function raised to the z times w bar, and this gives us the kernel centered at w, evaluated at z. Now, in this setting, Fox space functions have a very particular growth rate, and this is going to be used to show that a lot of the properties that people think hold for Koopman operators just don't. And so what we see is that if we take a look at the magnitude of g of z, then that can be written as g interproducted with kz, and taking the magnitude of that. And a little bit of Cauchy-Schwarz then shows us that the norm of g times the exponential function raised to the magnitude of z squared divided by 2 bounds the absolute value of g of z. The takeaway here is that g is an entire function that has at most order 2, and if it has order 2, it has type at most 1/2. So, for a fixed time step, in this case, it's going to be a rotation of the plane. Now, for x and y, if we were just in r squared, this would turn into multiplication by the rotation matrix, which is just a bunch of cosines and sines with a minus sign thrown in there at one of the spaces. But all of this gets compacted into just multiplication by e to the I theta when you're in the complex plane. That means that if I'm applying the Koopman operator to an observable from, say, my Fock space, then this really just becomes composing with e to the I theta times z. This will make it really easy to find a whole bunch of eigenfunctions and eigenvalues without really putting a whole lot of effort into it. And this leads me to our first counterexample. A lot of times when you see people talk about the eigenfunctions and eigenvalues for the Koopman operator, and this appears in applied Koopmanism and a few other places like review papers and other places that I've seen, and they claim that if you have two eigenfunctions with differing eigenvalues, then their product should be another eigenfunction whose eigenvalue is the product of the first two. Now, formally, this looks like it should work. If you were to take the product and, let's say, apply the Koopman operator to them, then you're going to move function composition onto the inside of each of these eigenfunctions, and then separately it looks like that's just the Koopman operator applied to each one of the eigenfunctions. So then you use the eigenfunction property, and ta-da, you're done. And this should work not only for these two, but any multiple collection of eigenfunctions. You should be able to multiply them all together and get new eigenfunctions, and so this is referred to as a lattice. It would work in the space of continuous functions, but we want to work over Hilbert space, and so when you're working over Hilbert space, it doesn't hold up so well. Hilbert spaces are generally spaces that look a lot like L2, and L2 functions, if you take their product, don't necessarily land back in L2. In L2, if you want to see an example, you just take 1 over the 4th root of x, and if you take its norm, then that's just the integral from 0 to 1 of, say, 1 over the square root of x, and that's finite. But if you were to take the product of 1 over the 4th root of x times 1 over the 4th root of x, you get 1 over the square root of x, and the norm of that should be the integral from 0 to 1 of 1 over x, which is infinite. So that's an example where we see in a Hilbert space, the product of two different functions doesn't necessarily land back in that space itself. But that has nothing to do with necessarily eigenfunctions of the Koopman operator, and I even said that we don't want to talk about L2. So what we're going to use is we're going to use this Fock space, and we're going to use the fact that we have this growth rate that we need to worry about. For this example, I'm going to fix our time step, or our theta rotation, to be pi. And that means that e to the I theta just becomes -1. So, if you want to see an example of an eigenfunction in this case, then pretty much any even function would work. If I were to take e to the z squared over 4, well, that is the same as e to the minus z squared divided by 4. And so this is an eigenfunction for the Koopman operator corresponding to rotation by pi, and it has an eigenvalue of 1. Now, we see that this is absolutely in our Fock space because it is an entire function and it has type less than 1/2, even though it has order 2. But if I were to take the product of this function with itself, then that gives me e to the z squared over 2. I'm not actually sure if that's in the Fock space or not. But if I were to take this product 3 times, then I get e to the 3/4 times z squared, and that definitely is not in the Fock space because it has type bigger than 1/2. So that tells you that we don't have a lattice of eigenfunctions because, well, here's a product that doesn't land back in the space, and our operator doesn't operate on things that aren't in the Hilbert space that is posed over. So that kills any idea of a lattice of eigenfunctions over a Hilbert space. So the next main misconception that I want to address is this whole idea of common eigenfunctions between these different Koopman operators. It appears in a lot of different places, and in particular, people try to use this to show that you'll have the same eigenfunctions for the Koopman operator as you do for the Koopman generator or the Liouville operator. And that just isn't true. If you take a look at the formal equations that you see in some of these places, you see this equation that is supposed to give you strong operator topology convergence to the Koopman generator. And so you see the limit as delta t goes to 0 of the Koopman operators corresponding to each one of those fixed time steps being applied to their eigenfunctions minus the eigenfunction divided by delta t. And then the idea is that you extract the eigenfunction by factoring it out, and then you're just left with this equation that is just resolved through, say, an exponential function or something like that. But there's something that's missing in that equation, and that is that the eigenfunctions themselves do depend on delta t. So you can't have just the same phi in both cases that you can factor out. It's going to change for every single delta t, and that causes real problems here. Here's an example where you can see that there are actually different eigenfunctions given different Koopman operators corresponding to different time steps. So what we're going to do is we're going to fix a particular time step, and we're going to fix it to be, say, pi over 2. And if you were to take pi over 2 and plug it into the polynomial z to the 4 minus z to the 8, and Fock space contains all the polynomials, so it's in our space, then you apply the Koopman operator to that function. What you're going to get is you're going to get e to the I pi over 2 times z raised to the 4th power minus e to the I pi over 2 times z raised to the 8th power. But we know that e to the I pi over 2 is really just I, and I to the 4 is just 1. So this ends up being an eigenfunction for this Koopman operator with that fixed time step with eigenfunction 1. Now, if I were to change the angle to be something that didn't really align with, say, pi over 2, but something that was, say, 2 pi over 3, then what I would get is I would try to plug this in, and, well, we don't get really nice, clean factoring here anymore. And so this z to the 4 minus z to the 8, that was previously an eigenfunction for a particular Koopman operator with eigenvalue 1, now it's not an eigenfunction for this new operator at all. It just sort of gets jumbled with coefficients, and that's not really helpful. So we see here that 2 different Koopman operators corresponding to different time steps, well, they don't have the same eigenfunctions. So now this brings us to our third misconception for the Koopman operator, and again, this is over the canvas of the Fock space. So generally speaking, a lot of results for the Koopman operator depend on the assumption that the Koopman operator is bounded. Now, that sometimes works, and if you're working on ergodic theory and living in L2, that's fine. But we know as far as sampling goes, we can't use L2, and so we need to be a little careful. So what we're going to do is we're going to take a look at the Koopman operator, and we're going to look at its adjoint applied to a kernel function. What this is going to do is going to give us a constraint on the operators, the Koopman operators, the dynamics that are allowed to give you a bounded operator. So in order to figure out what the adjoint of the Koopman operator does to a kernel function, it's pretty straightforward. You take a look at the functional, that maps G to the Koopman operator applied to G, interprodukted with a particular kernel function centered at Z. What that does is it changes G to G composed with F, and then the inner product against the kernel function just evaluates that at Z. Well, so then you have G of F of Z, and this turns into G interprodukted with the kernel function at F of Z. So that tells us that the Koopman operator, its adjoint applied to a kernel function centered at Z, is the kernel function at F of Z. So it advances the center of the kernel function. So one thing you should know about the symbols of the Koopman operator is that it can't change too much about these observables in a lot of qualitative ways. So it can't make a set of continuous observables suddenly discontinuous. So that means that the dynamics have to be continuous. And since we're over a space of entire functions, well, we're going to need the dynamics for the Koopman operator to also be entire. So that means that we can write it as a power series. This is going to be important in a second. So what we do is we take a look at the norm of the adjoint of the Koopman operator applied to kz, where that's the kernel function centered at Z. We take that norm, we square it, and we divide by the square of the norm of kz. On the top, we get e to the f of z squared divided by 2, and on the bottom we get e to the magnitude of z squared divided by 2. And so using your usual exponential rules, this is just real numbers, then we suddenly get this is equal to e to the f of z normed squared minus the norm of z squared divided by 2. And if this Koopman operator was bounded, then that means that this quantity can be bounded by some constant c. So what I'm going to do now is I'm going to take the logarithm of both sides. So on one side I have this difference of f and z divided by 2, and they're squares. And on the right hand side I have the logarithm of c. And I'm going to change z to its polar form, so it becomes r times e to the I theta. Now this is an arbitrary Koopman operator, so we're not really concerned with fixed thetas and all that anymore. This is just a variable. And so now I'm going to integrate this quantity, and I'm going to integrate from 0 to 2 pi d theta, and divide by 2 pi. On the right hand side it does nothing, so we just end up getting the natural log of c. But on the left hand side, a little bit of complex analysis will tell you that what you end up getting is you get 1/2 of the sum from n equals 0 to infinity of the coefficients, say fn, for the discrete time dynamics power series. And those quantities need to be squared, and then this is multiplied by r to the 2n, and then we're going to subtract this sum by r squared, and this quantity should be bounded by the natural log of c. However, if you let r go off to infinity, that power series isn't going to be cancelled by anything, so that can get arbitrarily large, but that would be a contradiction. And so it can't get arbitrarily large, and so that means that for anything beyond n equals 1, these coefficients have to be identically 0. And so what we're left with is just that f naught, the constant term, can stick around, and the linear term can stick around too, and that's because we have this minus r squared here. And so that means that if we're going to have a bounded Koopman operator over the Fock space, then it needs to be written as, say, f1z plus f0. And that's all of our bounded Koopman operators. Notice that this isn't even a particularly nonlinear system. This corresponds to a linear affine system. So when people are doing all this dynamic mode decomposition and working with Koopman operators, they almost always assume that they have a bounded Koopman operator. And this shows that this very rarely happens, at least over the Fock space. But I will tell you with certainty, it very rarely happens over any reproduced kernel Hilbert space, or any Hilbert space at all. The Koopman operators that are going to give you bounded symbols are always going to be incredibly restricted. And so you have to think of these in terms of being densely defined operators. There are plenty of densely defined Koopman operators that we can work with, and they're all going to be closed. And so you have to worry about your domain, and you just can't assume it's bounded. Okay, so this last misconception is probably the most concerning one, and it is really the lack of eigenfunctions. So here we're not looking at the Koopman operator, but the Koopman generator, and, well, it's also known as the Lie-level operator. If you want to find an eigenfunction for this operator, it comes down to resolving a separable differential equation. So if you apply the operator to some function g in our Fock space, then you get g prime of z times f of z is equal to lambda times g of z. I can give this to a differential equation student to solve, and basically you divide both sides by g and also by f, and then you get g prime over g is equal to lambda over f, and you do a little bit of integration, and you see that g of z now becomes g of 0 times e to the integral from 0 to z of lambda over f of w dw. And this is alarming. Since f has to be analytic, that means that if it has a 0, then that means it has a pole of some integer order, and that means it's not integrable. And so that means that this function isn't going to be continuous. And that means it can't be in our Fock space. And so whatever this function is, it isn't an eigenfunction for our operator, because our operator can only act on functions inside the space that we're working over, our canvas. Even if we change the canvas, we still have the same problem. We're generally going to be working with spaces of continuous functions, and, well, this isn't continuous. So I don't really know what to do about this particular one. And so this really concludes the last of the misconceptions I want to talk about. Now, on a positive note, none of these misconceptions really impact the way that people actually operate in the field. Very few people use the lattice of eigenfunctions in any practical way, and they get very good results. It's just the operator theory needs a little bit of retouching. Next time, what I want to talk to you about is how to do DMD without the Koopman operator, and we would like to use the Lie-level operator instead. And this is going to be a really exciting talk to give to you guys, and I'm not sure I could stay this calm for that one. Alright, so I'm going to go ahead and sign out now, and thank you for watching.